Looks good. Okay, so the University of Luxembourg can be described by these keywords: multilingual, personalized, and connected. It was founded in 2003, so it's very young university. It currently has around 6,200 students. But what is remarkable is that we have more than students coming from more than 100 countries. So this is a quite international place and environment. There are more than 500 PhD students, so the whole thing is very research oriented and research centered, because we believe that research is important, and this is the way to succeed. Then University of Luxembourg is well connected to the financial center and European institutions. So financial center, Luxembourg by itself is financial center of the world. Being a very tiny town, it has more than 150 banks and the associated industry. And for the European institution, we are very close to Brussels, and also a part of European Commission and European Court are located in Luxembourg. And what is unique about the university is the multilingual aspect. So the classes are taught in English, French, and German. French and German are more like for bachelor level, and English is for master and PhD. We have partners from more than 60 universities worldwide. And also what fosters international mobility is this. We have a mandatory semester for every bachelor student to be spent abroad. And the further students go, the more international it becomes. So this is working quite well, and because of this we have almost 3,000 international students. So out of 6,000 total students, so almost a half of students are international. These are very good numbers. So we have 3 faculties: the Faculty of Languages, Humanitarian Sciences, the Faculty of Law, Economics and Finance, the Faculty of Science, Technology and Communication is the 3rd one. And these faculties are reinforced by 2 research centers. One is S&T stands for Security, Reliability and Trust, and ALSSB. This is Research Center for System Biomedicine. So altogether, the vision is to remain small by the number of faculties, but the important point is small but focused. So this is the only way to succeed for a relatively small university, is to be focused and being results oriented. This slide just shares the budget that we had last year. This year we have increasing the budget, but the exact numbers will become available in a few months as the year ends. So last year we had almost 170 million euro, which is a good number, around 30.
Jealous enough. We can switch to something else, I guess.
Okay, as you wish. I have this beautiful picture, so it's a bit different from the budget, right? How the university looks like currently. So we are located in 5 different spots of the city. But what is good and what we are trying to do, we are trying to move from all these locations to something new. And this is our ambition project, which is worth 600 million. So build so-called City of Science to bring all faculties and research centers and consolidate in one place about 20 kilometers south from Luxembourg City. The good point is already almost finished, and we are almost ready to move there. The move is expected to is planned for summer 2015. So we are quite excited to find a new home in this place. So this brings me back to my original presentation, and now I would like to tell you what do we do in cloud computing at the University of Luxembourg, and how do we do it differently? The presentation doesn't go into detail, so the main focus of the presentation is to rather overview our activities and give a vision. But if you are interested in some of the topics that will be mentioned, just feel free to come back to me and chat. I would be more than happy with this. So speaking about the thematic activities, we have four main pillars related to cloud computing. So this is like cloud computing and cloud networking. Then the second direction is more like for cloud brokering. So when we try to optimize the provisioning of service from cloud providers to the customer, staying in between like a cloud broker. Then we work a lot into this generic field of robust, sustainable, efficient, distributed computing systems. So meaning that HPC, grid, and cloud. And finally, we are very active in information and document management related to big data, mainly in two fields, the field of finance and the field of biomass. So these are like top level overview. And then I would like to mention a few projects that we are running, just describing one line per project, just to give you a glimpse what we do. First is related to energy efficient communications in cloud computing. And we try to say that communications are important to consider, and they often determine the performance of cloud applications in this project. Then we have a project focused on multi-objective optimizations, so-called holistic view of the cloud computing systems. This one is a focus project, so it's focused on provisioning of voice over IP cloud services, and it's in cooperation with a company which mainly aims to provide voice over IP services for the cloud for companies like SMEs, small and medium-sized enterprises. So the idea is like when a company doesn't want to host telephone exchange on its premises, so it can just simply buy voice over IP phones, I don't know, from Cisco, for example, install them, connect to the network, and all the rest, including telephone exchange functionality, will be provided from the cloud. Then we have a project which is in the framework of cooperation between Luxembourg and Poland in internet shopping and cloud brokering field. This is a very nice one. It's about coordination of drone fleet. So if we have a fleet of drones, several drones, and they are given a certain task to implement, we design algorithms how for them to optimally do this, when they fly, not bump to each other and so on. And this has obvious military applications, but also civilian ones like surveillance, for example. And the last one in this list is focused on dynamic payload reconfiguration in satellite systems. So now, not to speak widely, I would like to focus just on one of them and give a little bit of vision on the first one, and give a little bit of vision of cloud computing. So a little bit of history, where it starts and where it heads. So before the year 2000, we had traditional IT, so just computers, workstations, servers. And then we started to talk about clouds. But cloud, since then, cloud started to come in different flavors. So first, it was mainly infrastructure as a service. And the previous presentation was mainly devoted to it, so I would not be detailing a lot about the infrastructure as a service. So it's when we want just to run virtual machines from the cloud. Then, a little bit later, we started to have platforms as a service coming from many providers, like, for example, Google, where we are offered intermediate language, a scripting language, which we can use to interface with cloud resources. And the rest of it is shielded from us as the customers, and done by the cloud provider, all the optimization all the associated processes. And then we came to the era of software as a service. Software as a service is where we consume, we don't care too much about what virtualized resources we use. We don't care about the techniques and the scripting languages we are involved to. But rather we are interested in consuming a real application. So I don't know, Facebook, webmail, whatever we use right now. And the last one, which is starting to be important around this time, is so-called business process as a service, where in a cloud fashion like we do with virtual machines, platforms, and services, we can benefit from the economy of scale and offer business processes. I don't know, for example, fund management to many companies. And then having this many flavors, we need to try to be sure what do we mean when we talk about cloud. And to help understanding about it, we can get a glimpse from the analysis of the market. So the cloud computing market is gonna be very big. So by the year 2020, it's expected to be $270 billion. But what is interesting here, is distribution of this. So it mostly will be software as a service, about 90% of the market. While business process as a service, platform as a service, and infrastructure as a service will remain tiny. And this makes an important turn in consideration when we consider cloud computing, because if we talk about cloud computing from now on, it's mainly about software as a service. So meaning that when we do resource allocation, when we develop energy efficient techniques, it's important to think about it as software as a service primarily. How did it appear that we have all this in the cloud computing in general? And commonly accepted point is that virtualization is an enabling technology. Virtualization of computing, of networking, of storage resources. So this is what made possible cloud computing. But think about it, virtualization is just a technique allowing us to share physical resources among several users efficiently. It's not a big deal, right? And the technology was already available long before. And then something else helps cloud computing to pump up. Virtualization is important, but something else is also crucial to have. And to find out what is something else, we can look into evolution of distributed computing systems. And we had four main steps in this road. We started with mainframes, then we moved to clusters, when people started to stack computing system in rooms. But still, capital investments were high at that moment, and the cost of hardware was high. So we said, okay, why don't we use grids? Why don't we get use of communication network and use already available infrastructure at different geographical location connecting by grid? And then we came in after the year 2000 to clouds. But there is a big difference between the first three and the last one, and the cloud. Because the first three are mainly related to computing. When we had a big computing task and a big computing job, and we wanted to cut it into tasks and send to different servers for execution. While the last one, clouds, they mainly work with clients. It's the other way around. Many clients, millions of clients come to the cloud computing system, and we need to serve them. So the processes and the goals are different. For example, in the first three, resources were the constraint. So we had more computing need to be done than available resources. While in the last one, in clouds, we have more resources, more servers than customers. Because if the other way around, if we have less customers, less servers than customers come into the system, we better buy more and not deny service. And what is important here, so it seems customers become important. So it's about connectivity, how to bring customers to the cloud. And this chart shows the relation between cost and broadband penetration of broadband connections. And somewhere around the year 2005, somewhere here, the cost went significantly down and the penetration started to come up. So simply, starting from somewhere here, we started to have customers able to connect to the cloud to consume cloud services. And this is where software as a service came up. So this gives understanding how and why do we have software as a service so big in the market share. Another thing, if we look into evolution of devices, of different consumer devices, there are two trends. The first is the size becomes smaller. Smaller size means constraint on computing resources, constraint on storage, and on the battery life. And the battery life gives a constraint to basically all of that, computing, storage, and network. And the other trend is that devices are starting to be, all of them, mobile. Mobile meaning they need wireless connections. So let's look what happened in evolution of wireless systems. And they started around mid-90s, probably. And the first wireless system, like the first generation or the second, the first generation was analog. And then from the second, we started to have digital. But still, the data rates were very small, and they were barely enough to carry a phone call. And maybe starting from 3G, the data rates and then some connectivity started to be enough to send data objects, which is essential for cloud computing. And it's by the time it's aligned with this around the year, somewhere in in 2005, 2004, approximately. And this is where the first gadgets started to appear. So this all aligns. And to kind of follow up on this, so it seems communications are important in cloud computing. Trying to follow up on this, we analyzed a lot of cloud applications, different kinds of them, Google Apps, Facebook, and Twitter, and other. And we categorized them into a large number of categories. So, for example, cloud storage, video streaming, online office, or video conferencing. And we just checked what kind of requirements each of these categories have against computing power, bandwidth, communication delay, degree of interactivity, and storage. And it came up that all of them, without any exception, they needed at least one of these three highlighted, which are related to communication. So give you an example. For example, cloud storage and cloud backup are very in need for bandwidth, but they are not so much sensitive to the delay. So high delay is okay for backup. But for example, voice conferencing, like Skype, doesn't care too much about the bandwidth because the bandwidth requirement is very, very small. But delay makes sense. So if we start having large delays, so we start hearing this, and the voice quality goes down. While, for example, cloud gaming, which means rendering the server, is hungry for almost all the resources. The only exception in this chart is the last one, HPC, high-performance computing applications, which is a pure big computing, meaning that, for example, the calculation of the evolution of the universe, or more civilian, more common example is calculation of weather forecasts models as we do every day. So for this, we work a lot on optimizing communication in cloud computing, taking an approach for developing novel solutions in network hardware, meaning switches, routers, links, and all around this. Then the data center communication system as well, and the protocols. And we came up to something, when we started to work on this, we finally found that there are no metrics exist. So we started to work on metrics first. There were no metrics at that moment to measure efficiency of communication systems in cloud computing. And we developed a comprehensive set of metrics for doing that, so it's already available. Give you an example. For example, to know efficiency of cloud of communication system, you can access it by measuring the amount, the number of joules spent for delivering certain number of bits of information. So the number of joules per bit, for example. Or to know the efficiency of communication equipment, energy efficiency of communication equipment, we can measure the degree of energy proportionality, meaning that how much the consumption, energy consumption increases if we increase the load, and how linear it is, the linearity of this process. So as soon as metrics were in place, we started to work on this, making the network hardware more efficient. And there are two trends in these two main roads to go. First is making the hardware more energy proportional, so you can scale the load and the consumption will scale. And second is integrate network hardware with communication protocols, or not integrate completely, but at least make them aware of the protocols processes. It helps a lot to optimize. Then working on the data center communication systems. So the main focus is on energy efficient network aware resource allocation and multi-objective optimization. So these are the two main streams. So finally, we're currently working on design of energy efficient communication protocols, because everybody knows that TCP/IP was designed in the late 70s, beginning of 80s. At that time, we didn't have cloud computing at all, and energy efficiency was not a concern. So obviously, TCP/IP currently is not optimized for this, and there's a big niche for optimization. While developing different scientific techniques, we always need to evaluate them to see if they work or not and how good they are. For this, there are two possibilities where you just own a big, computing infrastructure just to test your techniques, which is a bit expensive. But there is another way, and we have taken it. So we developed a comprehensive simulation framework, which is called Green Cloud. Currently, it's one of the leading cloud computing simulation platforms. So in this platform, you can actually simulate a data center or several data centers. You can put loads on servers and measure things on component level and measure things very precise. So it makes it's a precious tool for research indeed. So these are just a few screenshots. So for example, this is a screenshot with results with the energy allocation between different components in data center, and a bunch of charts which goes all the way down with all the nitty-gritty details of the simulation. We have pluggable energy models, and for example, the simplest one for the servers looks like this. There is a fixed part associated with motherboard, peripheral disks, and so on, and there is a variable part which is dependent on frequency, which describes the CPU energy consumption. And this is in line with simulation of, for example, this techniques such as DVFS, dynamic voltage and frequency scaling. But obviously not only servers consume energy, and we also have models for switches. In a similar way, we have fixed parts for consumption, like for example, the power associated with switch chassis or switch line cards, and variable part, which is associated with ports. And in switches, in network switches, we can do similar things to adaptation of the frequency. So we, like we do in processors, we can degrade the line rate to make it consume less if we don't need a full speed. So, for example, the example of energy efficient resource allocation technique is just one of them. I'm not going into mass, but it's just extract from one of the solutions that we developed. Has a part of the function related to the server looks like this. So it has very, let's say, reduced probability of selecting servers with a very light load. The reason for that is for energy saving, we would like to consolidate the workload on a minimum amount of servers. So if the server is loaded on 10–20%, it has high probability that the task will finish and this server will become idle, so we can put it into sleep. While if the server is already loaded for half and more, so it's not very high probability that it will become idle, so we just load it till the end to have a full load. Again, not a very full load. We can have a safety margin not to overload the server, and this is controllable. But again, servers are not the only thing which we take into consideration while doing resource allocation. This is the first thing to consider, but not the only. Another important thing is networking. And for this, again, not going into mass, the important things are to consider the link load, the load of the link between servers, between racks, between pods in data center. But also, a link might not tell you much because you can have almost 100% loaded link, but still your packets can go through very fast without incurring additional delay. What is important to consider in addition to the link load is the queue occupancy, because most of the delay comes from packets waiting in queues. So if the queue is already full, it might not be a good idea to send there more packets, if you have an alternative, of course. And it plays an important role when you select your server for your next task execution. So what we work on is this. Primarily, it is 3-tier factory data center infrastructures. So when you have racks, they are connected by aggregation switches forming pods, and then all of them are connected with core switches. So the data center following this architecture usually looks like this. So these are, servers are put into racks, racks put into rows, then they are closed, and so on. But also, we work on future data center architectures, and when data center components look like this, so when we have this container-based data centers, when inside a container you have a large number of components, it becomes a problem of reliability. If a component fails, let's say a CPU of a given server fails inside this container, it is not possible to go inside and to change it. So we need to live with failures. We need to make things tolerant to failures. And the only way to do so is to design architectures that a failure would not bring down a big part of the data center. So we need to rely on distributed data center architectures. And to name a few, they are, for example, DCell, DQ, PyCon, where a single failure doesn't bring a big part. So it can be a failure of a switch will bring down the switch itself, but will not bring down the whole rack. Okay, let me skip maybe the next slide. Oh yeah, just to mention that this simulation environment is fully available. So you can, if you'd like, you can download and try. And it comes in two variants, as a source code or a pre-installed virtual machine, just to use the trial. But finally, I would like to say that cloud computing is not only about data centers and about task allocation inside data centers. What we are currently doing is this. We consider clouds and cloud processes all the way down to the end user. And the end user, cloud users right now are mostly on mobile devices. At least the majority of them. And they come like connected through wireless providers. It can be ad hoc connections, vehicle network connections. So there's a lot of infrastructure between the device and the cloud itself where the computing servers are located. And it is very important when scheduling things, doing resource allocation or optimizing the cloud performance, is to consider the whole infrastructure that is in between, because this is what defines the application performance. So the message from this is that cloud computing started with the emphasis on computing, but right now it seems communication is becoming important and sometimes even defining the performance of cloud applications. Okay, good. Thank you.